Welcome to lecture 18, which is going to be on drag forces. That means air drag or air resistance, you might also call it, but also say drag in water, for example. So we'll start with some examples about air drag, talk about how to mathematically describe this type of interaction, this type of force, and then we'll look at some examples and applications to essentially see the consequences of it, because it is somewhat unique in that the strength of the force of air drag depends on the velocity. And in the course of this, we'll also discuss this concept of terminal velocity. Okay. So let's make some observations. Let's just sort of explore a little bit what we mean by air drag. So imagine you're cycling. Here, this is my beautiful picture of somebody cycling, and you're cycling along fairly slowly. And it's fairly easy to do. It's easy to go at a slow, constant speed. You pedal a little bit, but it's not very hard work. Now, on the other hand, if you want to go really fast, you need to pedal a lot harder. It's much harder. It's much more difficult to do that, even though you're not trying to speed up further. You're not trying to have acceleration. You're just trying to maintain your very high speed. Now, given that we know about Newton's second law, that force relates to acceleration, not velocity, it shouldn't really matter how fast you're going, right? The only thing that should matter for how much you have to pedal is, well, are you trying to speed up and at what rate? But of course, air drag gets in the way, right? You can feel it when you cycle. We could have used the example of a car, but when you cycle, you can actually feel the air drag hitting you. And you just have to overcome, you have to counteract this drag force of the air hitting you by pedaling harder. Right, it's not easy to do when you're going low speed. Other examples, skydiving. Right, so here you are falling, jumping, and it's going to go pretty fast. Well, once you open your parachute, you're going to slow down significantly. Why is that? How can you explain that? Wind tunnels, what are those about when they test some new shape of a car or plane, put in a wind tunnel, we see sort of streamlines of colored air going across it. What's that about? Like how does that relate to what we're learning and to the drag force? Another example to look at is rocks. So a rock might be falling in the air and it's going to fall fairly fast. I mean, we know free fall, constant acceleration, but there's air, the air is going to create a drag force and slow it down. So here's a rock falling on this poor little fella down here. On the other hand, if we drop that same rock in water, there's a boat up there, it's underwater, well, it's going to sink a lot more slowly, even though it has the same weight. What is the difference between those two? So all of those ideas are explained by one single concept, that is the notion of drag forces. So this is what they look like. This is mathematically how to describe them. Let me talk you through it. Of course, on the left-hand side, F drag, well, that is literally just the drag force. Now notice I've written it as a vector. It has a direction as well as a strength. Now on the right-hand side of this equation that describes drag forces, we have V, that's the velocity, and B. I'll talk about B in just a second. This is some constant. But there's a minus sign in here too. So what does that mean? That means that the direction of the drag force is going to be minus the direction of the velocity. It's going to be the opposite direction. So the minus sign, do it here. From that we can read that this vector is the opposite direction of this vector. Of course, assuming B is positive, a positive number, which it is. So that's what a minus sign means. F drag, we write out drag force in opposite direction of velocity. What does that mean? Well, it means that if you're going cycling east, the drag force is going to push you west. Like if you're cycling forward, the drag force, the air resistance is pushing you backwards. I think that's very intuitive, right? It opposes the direction you're going in. It doesn't matter if you're speeding up or slowing down. At that particular instant, it will always oppose the velocity. It's a little bit like kinetic friction in that regard, except that kinetic friction is just constant. Depends on the coefficient of kinetic friction and the normal force between the surfaces. Not here. Here, the strength of the force depends on the velocity itself. The last piece is this constant, right? So we're saying F is minus velocity times some constant. What is this constant? This constant is called the drag coefficient. It really just encodes drag coefficient is a single one. This one, drag coefficient. It encodes the other factors that affect the strength of the drag force. So what is that? It's determined by the size of the object. If you've got a bigger object, more surface area, that means you're going to get more drag, even if you're going at the same speed. But not just the size, but also the shape. For example, a flat front of an object is going to have more air drag than the same front area, but sort of shaped in what we might call an aerodynamic way. So this is kind of where the wind tunnels come in, right? To test different shapes for how much drag do you get for a given velocity. But there are other factors too. One main one I think that to list here is the substance you're in, the fluid you're in, or the object is in. For example, could be air versus water, right? You're going to have different amounts of drag in air versus water. This is where the falling rock comes in, where if the rock falls in air, right, the drag force is less, so you're going to get to a higher velocity before drag cancels out weight, whereas in the water you're going to get more drag force at lower velocities because this number is bigger. And let's look at it in action by looking at the first example. We had the cyclist in some more detail. So here's the example. We're saying a cyclist pedals with a constant force, and that creates 100 newtons of a forward force. Now, what is this force? It's essentially, ultimately, what makes the bike go forward is the friction with the ground. It's static friction, because the part of the tire that's touching the ground isn't sliding. We can talk about it more in class. How is friction creating this forward force? So we're getting a forward force of 100 newtons. Now, let's suppose our cyclist with the bike, all in one, is 50 kilograms. So maybe it's a child with a child's bike together. And the drag coefficient is 25 newtons per meter per second, right? It's force per velocity. That's what the units of B are. Make sure you can make sense of that with regards to the equation F equals minus BV. Of course, I could rewrite this because a newton is a kilogram meter per second squared. I could actually rewrite this as kilogram per second, but it's kind of, I find it hard to interpret this, right? So newtons per meter per second is sort of easy to understand as force per velocity. Okay, I just sort of made those values up, of course, just to have a concrete example. So what's going to happen? Initially, our cyclist starts at rest. Right, so here's my cyclist. Now the cyclist, of course, has a weight and a normal force, because otherwise it'd fall into the earth and so on. I'm going to ignore those because they're boring. Right, they're up and down, opposite, equally, with equal strength. So we're pedaling forward. So this is the force that propels us forward. Let me call this F pedal. Of course, it's really the force of friction with the ground, but I'm going to make it clear that it's due to us pedaling. That's constant. It's a constant 100 newtons. Right. So when we're at rest, right at the beginning, I'm going to have a net force of 100 newtons. Right, because this force is 100 newtons. So I'm going to have an acceleration of F net divided by m. m is 50 kilograms, so 100 over 50, that's 2 meters per second squared. Okay, fantastic. So we're starting to go forward. So a little bit later, we're no longer at rest. Now we are going, say 1 meter per second. You know, a fraction of a second later, we're now going 1 meter per second. Okay, what's happening now? Well, you're still pedaling with the same force as before, so that hasn't changed. But now in addition, there's air drag. Right, there's air drag, and air drag opposes velocity, it's backwards. Now what is the drag force? Well, it's minus b times v. Well, minus is minus, b is 25, right? It's determined by essentially the shape and the size of the cyclist, the fact that the cyclist is cycling in air and not underwater. All those things are determining this to be 25. Ultimately, I made up the 25, but whatever that number is in real life for a particular cyclist, well, this is how it comes about, right? Shape, size, air, so on. So 25 newtons per meter per second times, well, we're going 1 meter per second times 1 meter per second, and that leaves me the drag force with minus 25 newtons. Makes sense, right? 25 newtons per meter per second, and we're going exactly 1 meter per second. So that means my net force is now less. Right, this is still 100, this is 25, so F net is equal to 100 newtons forward, 25 newtons backward, so I have to take those away, makes 75 newtons. Alright, well, that implies that my acceleration, that's the net force divided by the mass. The net force is 75 newtons. The mass is still 50 kilograms. That hasn't changed. So 75 over 50 makes 1.5 meters per second squared. So we're still accelerating, right? We started off accelerating here, but we're now accelerating at a lower rate. So you're still speeding up, but not as quickly as before. Now suppose a little bit later, the time passes, maybe another fraction of a second, maybe roughly a second, and we're going to end up at going at a speed of 2 meters per second, right? We were going 0, 1, now we're going 2. Took a bit longer to get from here to here than to get from here to here because our acceleration was lower during the next interval. But we're going faster, so our drag force is going to increase. Our pedal force hasn't changed, but our drag force is now bigger than it was up here because we're going faster. We're going to make the arrow a bit bigger. So we're going to go through the same steps, and I find the drag force is minus BV. Let's do the math. 25B, right? 25 times 2, because now we're going 2. So 20B is 25 multiplied by 2, because that's my velocity. So the drag force is minus 50 newtons. Well, that makes the net force equal to, well, it's 100 newtons forward, pedaling, but then 50 newtons backward, so that leaves me with 50 newtons of net force. Okay, that makes the acceleration, the net force divided by the mass, F net over m, 50 newtons forward. Notice the 50 newtons I'm plugging in is the net force, not the drag force. The drag force is backwards, but 100 minus 50 happens to be also 50. Divided by 50 kilograms leaves me with exactly 1 meter per second squared. So now we are still going, we're still accelerating, we're still speeding up, but even less so than we did before, because there's a bigger force pushing us back. Now you can figure out what happens at v equals 3, right? You figure that one out yourselves. It's fairly straightforward. You'll find that you'll be still accelerating, but now at 0.5 meters per second squared. So make sure you understand why, right? Make sure you can go through the steps for this one here. And eventually, you'll be going 4 meters per second squared. So at this point, what happens? Well, if the same forces still apply, so pedaling, which of course ultimately the force that makes you move is the friction. Yes, we know that. It's going to be a fairly substantial drag force pushing you back because you're going faster, right? How big is the drag force? Let's have a look. Well, minus BV, which is minus 25 times 4, because we're going 4 meters per second. So that comes to minus 100 newtons. So what's the net force? Well, we're going forward with 100, pedaling with 100 newtons. The drag is 100 newtons, so the net force is 100 newtons minus 100 newtons, which is 0. And so then the conclusion is that the acceleration is also 0. So we are no longer speeding up or slowing down at this point. Well, we were never slowing down. We're no longer speeding up, right? We've reached a constant final velocity. And we call that velocity the terminal velocity. Let me write this down. So at v equals 4 meters per second, the cyclist is no longer speeding up. I'm going to write no longer changing their velocity. Because the drag force is equal in strength to the force that's propelling the cyclist forward, in this case the pedaling, the friction with the ground. I'm just going to call it the forward pushing force. So this velocity, this final velocity where it's no longer changing, right now we are stuck at 4 meters per second because there's 0 acceleration now. We call it the terminal velocity. So 4 meters per second is the terminal velocity. Right, that's the term we're defining here. Terminal velocity, the speed or the velocity at which you're going, such that the air drag exactly cancels out whatever force it was that made you accelerate initially. Okay, let's look at a quick other example that's kind of similar. So here, let's imagine a skydiving. So I just started writing this out. And we're just out of the plane. So we're jumping out of a plane with a parachute, but the parachute isn't open yet. The instant we leave the plane, or maybe it's a helicopter just hovering there, so we don't have to worry about sideways motion. The instant we're leaving, our velocity is 0. We're just dropping. Right? We haven't had time to accelerate yet. So if the velocity is 0, then because F equals minus BV, well, if V is 0, the drag force is 0. Right? So my free body diagram looks like this. There's weight down and not much else. So my acceleration is the weight. Right? This is the weight. mg. And I divide it by the mass. That leaves me with g. It's like free fall. It's a free fall, acceleration g, because my weight is mg divided by m Newton second law. Okay, so that means you're speeding up a little bit later. You have a later. My handwriting is getting worse and worse as time goes by, apparently. So now we have some velocity. I'm going to write some. Not much, just a little bit. So that means you've got a bit of drag force. Okay, so what does my free body diagram look like? The weight doesn't change, right? The weight is always the same. It's mg. mg mg. But now there's a little bit of a drag force backwards. It's not very much. It's like this. A little bit of a drag force right there. So that means I have an acceleration A. It's going to be smaller than g, because A is the net force, which is mg, the weight down, minus the drag divided by m, which I can rewrite as g minus the drag force over m, right? So what does that imply? Well, that implies that the acceleration now is a little bit less than g, because it's g minus whatever the drag force is over m. And so then this keeps going, we keep speeding up, and so the drag force keeps getting bigger. Right, so they can draw the same picture essentially, but with a bigger drag force. So as time goes by, the weight does not change, that's the force that made you go initially, but the drag force has increased. So if here the net force is still like this, not quite as big as the weight, a little bit smaller, then now the net force here might be like this. It's a lot smaller now. It's still down, the weight is still bigger than the air drag, but not by as much. And so eventually, because we keep speeding up, the drag force keeps increasing until we are at the point where the weight, mg, is equal to the drag force. At that point, the net force is 0. And so that means there's no acceleration here. And we've reached terminal velocity. Okay, so then what happens? So now we are falling at a constant speed, because I've reached that speed falling where the my weight is equal to drag force. And I keep forgetting at what speed it is for a human body falling through air, but it's of the order of like 100 meters per second. It takes you a few seconds to get there, to reach terminal speed. And then what happens? So now we're going to open our parachute. So now open parachute. What does that imply? Well, that implies B, the value of B, suddenly gets a lot bigger, because we've increased our surface area and have a very non-aerodynamic shape. So what does that imply? It means suddenly, because we're still going this terminal velocity that we had, suddenly, the instant we open our parachute, well, my weight is still what it was, that's still mg, but say if I increase the B value by 10, because I suddenly have that much surface area from a parachute, suddenly the drag might look like this. So you feel a net force upwards. You feel this sort of lurch upwards. So you're getting pulled upwards really hard. So the acceleration is up. Implies acceleration is upwards. The acceleration being upwards means we're slowing down, because we're going down. We're moving downwards, so upwards acceleration means we're slowing down. And then we'll slow down, and that will decrease the drag. And that happens very fast, of course. Within, a couple of seconds at most. So that implies we're slowing down because of the upwards acceleration. It's opposing the direction we're going in. So we're slowing down. That means the drag force gets smaller. Right, and then eventually, it might get smaller, but there's still net force up. Eventually, we reach a new terminal velocity. It's a lot lower. This is the with parachute terminal velocity. So in both cases, before we open our parachute and after we open our parachute, the weight is the same. So for terminal velocity, the drag force is the same, right? The drag force, and you're falling fast without a parachute open, is the same as the drag force when we are descending slowly with the parachute open. The difference is that that in one case the B value is big and the V value is small, in the other case it's the other way around. So let's write this down. Before opening the parachute, we are like this. Weight down, drag up, and they're equal, right? While going at terminal velocity. Afterwards, after the parachute has been open for a couple of seconds, so after a bit later, so we had time to reach a new terminal velocity. After doing that, the diagram, the free body diagram, looks exactly the same. Because my weight hasn't changed, that the Earth doesn't care, and my terminal velocity, well, it still means the drag force cancels out the weight. So what's different? In this one here, I've got big V, small b, make up this one. Down here, I have a big B and a small v, right? And my V here, my B is bigger because I've got a big surface area, big parachute. So a smaller V will be my terminal velocity. Whereas here, I'm fairly aerodynamic, at least a lot more than with the parachute open. So to get that same drag force, I need a much higher value of V, because B times V, that is in both cases equal to mg. Let me draw this on a graph for you, what that looks like in terms of the velocity. Let's say I'm going to draw a velocity versus time graph. I'm not going to care about values. I'm just going to plot it. So we start at 0, right? We're jumping out of the plane. So now we are falling and we're increasing our velocity with a rate that is equal to g, because we're in free fall. So that means right down here, the slope is equal to g, right here. But then, as we are speeding up, as our velocity goes up, our acceleration goes down because the net force is getting smaller and smaller and smaller as the drag force gets bigger, and so the slope gradually decreases. It becomes flatter and flatter and flatter and flatter. Eventually, essentially constant. And this is my terminal velocity. Right? And now, if we keep going, if we could fall forever, we just keep going at a constant terminal velocity because the forces cancel each other out. Weight down, drag force up, net force is 0. But now, say we're opening parachute. Right here. So what happens now? Now suddenly, we're in the situation where the drag force is a lot bigger. Because I've just opened my parachute. So there's a big net force up. Big net force up means we're slowing down, right? So because the velocity is of course measured downwards. So we're slowing down quite rapidly like this. But as we're slowing down, the drag force decreases, and so the slope sort of gets less and less and less until we reach a new terminal velocity. Down here. And at this point, the drag force is once again equal to the weight, but it's made up differently, right? B is big, V is small up here, and V is bigger, but B was smaller, and that's how you end up with the same drag force in both cases. And eventually then you hit the ground. If we drawn that graph for the cyclist, well, we would have stopped right there because there was no parachute, but we would have seen the same shape, steep at the beginning, where most of the pedal force causes acceleration, is left over as net force, and as we get faster and faster, there's more drag force backwards, and so there is there's less net force, and so the acceleration is lower. The slope of my velocity time graph is smaller. Okay, one last thing to think about with air drag is the notion of something like wind. Now, wind, you're like, well, if I'm out on the water with my sailboat, and I don't have a sailboat, but if you imagine having a sailboat, you're out in the water with your sailboat, and wind blows into your sail. Now you're like, but I'm not moving yet. I'm stationary, and suddenly there's a gust of wind. Well, if the wind blows east, that's the same as the boat moving west through air. Like the relative motion is the same. And so you would calculate the force on your boat in just the same way, but the V is measured relative to the air. And if the air is going 10 miles per hour right, but your boat is stationary on the water, well then that's the same force as if you were going 10 miles per hour left through still air. Hopefully that makes sense to you. Think about it a little bit more as a sort of exercise that you can make sense of that idea. Then you can find what it takes for the boat, like what the terminal velocity of the boat might be and how you might think about that concept. Alright, that's enough from me. Have fun putting all of this into action, and I'll see you in class.